Okay, let's get started. So we're going to have our midterm on Wednesday. So it will last 2 days. Okay, so normally it'll start on 9 a.m. and then you can download it and try to finish it. So it will be due on the 9 a.m. on Friday. Yes.
Are you writing the midterm or is it questions from the book?
Oh, I'm writing it.
Okay.
Yeah. So yeah, you can use the homework as a good exercise, but normally the exam would be easier than the homework problem. It would be very basic. So yeah, it was designed for 2 hours, but I think if you are fluent with the concept, yeah, you should be able to finish it maybe within 1 hour for sure. Okay, so yeah, it's not very difficult. All right, so any questions? Okay, and do not use ChatGPT. So I have an algorithm. So there's a professor here. I think Mark is not here, so probably took his class before. He taught information theory and machine learning. So but he left. So he has a very good program that can detect whether your answer is generated by ChatGPT or not, right? So yeah, but if you you change it a lot, probably we cannot detect, right? But just try. I mean, the problem is not difficult. Just try to not use ChatGPT. Okay. Yeah, it's a good test for your capability on information theory. Okay, so yeah, let's review what we. Any questions? Yes.
How many questions are on
5 questions. Yes. You have a question? Okay. Oh. Okay, so yeah, let's see. So we'll have one problem on channel capacity. So basically, until now, what we learned is how to compute the capacity, right? It's a maximization of the mutual information, right? How to maximize it, right? So we introduce a number of methods, right? So we can try uniform distribution for the input and see whether y follow uniform distribution or not, and so on. And also you can use the approach that we're going to introduce. We introduced last time, and then we're going to continue talking about that today. So there'll be one problem on channel capacity, yeah, and 4 problems from the previous chapters. Okay, yeah. Any other questions? Okay, great. So let's review what we covered in our last lecture. So in our last lecture, we continue talking about examples of channel capacity, right? And then we show you, okay, in general, how can we solve the problem of the maximization of mutual information, right? And so in the last lecture, we see how to compute channel capacity for symmetric channels, right? And we define 2 kinds of symmetric channel. One is the sum of the row and sum of the column for the channel. So sorry, not sum. I mean the row is a permutation of the first row, and the column is a permutation of the first column, right? Then, yeah, for this strong symmetric channel, so we compute the capacity, right, which is given by this guy, right, and this R is basically the entropy of the row of each row, right? Because each row is a permutation of any other row, then it doesn't matter which R it is, right? They're all the same, right? And the property of the the column here is that we just use the property that the sum of all the columns are the same, right? So we didn't use one is a permutation of the other one, okay? And then we consider the weakly symmetric channel, right? So basically, for the weakly symmetric channel, we only have the requirement for the row, not the column, right? So each row is a permutation of the first row. Then the capacity is given by this, right? And also, let's see whether we have it. Oh, it's not here. If this relationship is satisfied here for this guy as well, right? And for the first term, so it's also given by log y. Okay, so you can try it. So basically, if our relationship is over this finite field, then no matter what kind of input distribution there is, output is always uniform. Okay, you can show that. Okay, and then we go back to the most general case, right? So how can we maximize the mutual information in general, right? So basically, what we do here is that we kind of say that before, mentioned that before in the very beginning, right? So for mutual information, so we have 2 variables to consider, right? One is a variable of this p here, right, which is the input distribution, where this p is a transition distribution, right? P y given x, right? We say, okay, if this guy is fixed, then mutual information is a concave function of this guy, right? Vice versa, if this guy is fixed, then the mutual information is a convex function of this guy, okay? So in this channel capacity problem, what we use is the first property, right? So when this guy is fixed, then mutual information is a concave function of this guy, right? And then we can rewrite this as that. You can see here is if PRS is fixed, then it's a function of PR, right? And then our constraint is that summation of PR equals to 1, and then the PR is between 0 and 1, right? If that is the case, then so this is a typical convex optimization problem, right? So it's maximization of a concave function, right? So basically what to do is that we use the KKT condition, right? And maybe, so we can see our notes here. So basically, let's see. So we start from here, right? So basically, we're going to use the KKT condition. So what we do is that we write the objective function and minus lambda times the constraint here, right? Lambda is nothing but the Lagrange multiplier, right? Then we'll have this guy, okay? And this is a simple case, right? So we can see that, you know, if so PR is bigger than or equal to 0, then, you know, so we're here. So basically, this basically means that the derivative of this guy is equal to 0, right? But when PR is here, right, the optimal value is here, then our requirement is that PR is bigger than or equal to 0. Then you can see this guy is optimal, right? In this case, okay, so we need to make sure that the derivative of fx here, the derivative of this function here is less than 0, right? So basically, that's a result from the KKT condition, right? KKT condition is kind of more complicated than this, right? Okay, and then so by solving this kind of problem, yeah. So this theorem tells you that okay, officially we have this for our problem, right? So basically, if x is bigger than 0, and then so this guy equals to 0, otherwise this guy is less than 0, right? And then we do the derivative of the j function, and then we can get this, right? And then we just, you know, because we know mutual information, we just compute that, you know, precisely. And then basically what we got is that the derivative of this guy is nothing but, so the mutual information when x equals to r and y, and minus 1 minus lambda, okay? And then we can see that, so based on the condition we talk about, when PR is bigger than 0, and this guy, so basically this guy will equal to 0, right? And then, so therefore, this mutual information is equal to 1 plus lambda, right? When PR is equal to 0, then we can see that this guy is less than or equal to 1 minus lambda. Yeah, 1 plus lambda, not minus. Yeah, this is a plus. Okay, 1 plus lambda. Okay, and in this case, we can compute the channel capacity here. So we denote that by C prime, and then we can see that channel capacity is nothing but 1 plus lambda, right? And the beauty here is the follows, right? So from here, yeah, we just finished it here. So from here, we can see that, so when PR is bigger than 0, so all the mutual information is the same, equals to 1 plus lambda, right? When PR equals to 0, and this guy is less than 1 plus lambda. So what does that tell you? It tells you that, okay, when PR equals to 0, we should not use this R, right? Because in this case, the capacity, I mean, this mutual information is less than or equal to 1 plus lambda, right? We should not use it. We should only use that because that is the maximum value. And it's equal for all x. Does that make sense? Does that make sense? Okay, and therefore, you know, this will give us the following theorem. So let's see what we're going to cover for today. So today is our lecture number 27, and we're going to, the first we're going to cover is again this optimization theorem. Optimization theorem, and then we're going to cover the joint typical sequences. Okay, or we call that the joint AEP. Okay, so if we can finish that, and then we'll start talking about the channel capacity. So we'll start the proof of the channel capacity to see why it is equal to the maximization of the mutual information over the input distribution. Okay, that's the agenda for today. Okay, let's introduce the theorem that what is the distribution that will maximize the mutual information. Okay, so from what we just covered, so we can see that the optimal input distribution, so we denote that as P star X equals to PR star. Okay, so this must satisfy the following condition. Okay, the first one is that if P star is bigger than 0, and then this mutual information when x equals to small x and y, so this has to equals to what? 1 plus lambda, right? But everything equals to 1 plus lambda. It doesn't matter what value that is, right? The point is that, so there has to be the same, equals to c prime, right? So otherwise, so if P star equal to 0, right, here is bigger than 0, if equal to 0, then the mutual information of this guy will be less than or equal to c prime. Right, so this is just a restate on what we just computed. All right? Okay, so here we can see that, so now we can have two categories of the codebook or the input letters, right? So if x equal to this guy, and then, so the mutual information for each of them are the same, and they achieve the highest number, the largest number, right? But if we use this x to compute it here, then, so this guy may be less than c prime, which is not good, right? Therefore, we say, okay, for all x, we have some good letters, and we have some bad letters, right? So now, for all the alphabet, input alphabet x, so it's a union of the x0 and the x1, okay? So we denote x0 as the good letters, as the bad letters, x1 as good letters. So this is for all x such that px star equal to 0. And for x1, so that's all x such that px star bigger than 0. Okay, and we say these are good letters. Those are bad letters. That makes sense? Okay, therefore, from this theorem, so it basically tells us that in practice, we should only use good letters and we should not use bad letters, right? Because for bad letters, the optimal distribution for that is px star equal to 0, right? It should not appear at all. And the mutual information for those is less than c prime. That makes sense? Okay, let's write it down. So this basically means that, yeah, what's that? Why is, do you know what that is? This basically means that we should only use good letters because the optimal distribution for those letters is bigger than 0. Right? And therefore, the mutual information equals to the maximum number. And we should not use bad letters, where the optimal distribution for the bad letters equals 0. Why is it always raining? Maybe I can turn it off. No. Okay. Yeah, so this is the beauty of the using the KKT condition to solve this problem, right? So yeah.
This might be a stupid question, but why are some letters good letters and some letters bad letters?
Yeah, this is the reason. Yeah, for the good letters, you have the mutual information equal to C prime, but for bad letters, the mutual information are less than that.
Yeah, I understand. But I don't understand why the mutual information changes based on the input or like the distribution.
You don't understand what?
So it's like the mutual information, the distribution of the maximum value of the mutual information changes based on the input, right?
Exactly.
Why does it change?
Why does it? Oh, because the definition, right? So mutual information. Yeah, let me show if. Yeah, this is the definition of the mutual information, right? So it's a function of PR.
Okay.
This is the input distribution.
Okay.
Right. So. Yeah, or the mutual information between x and y is the mutual information between the distribution of x and distribution of y. Oh, yeah, not exactly. I mean, you know what I mean, right? So basically, in other words, so it's a KL divergence between the joint distribution pxy and the product of the individual distribution px times py, right? So it's a function of px. Okay, great. Yeah. What I was trying to say is that so normally for the KKT condition, it cannot give you the analytical solution, right? If you want to solve the problem, normally still have to go to probably the green descent or whatever Newton's method, right? But through this analysis for this particular problem, so we can get very good, or we can have a good understanding for the structure of the solution, right? For structure, you can see that, okay, so basically for all the x that's px bigger than 0, then all this mutual information has to be equal, right? So it doesn't matter what C prime is, right? The point is that they all have to be equal, right? And for all other mutual information that is less than that, we do not use them at all, right? Px star is equal to 0. Okay, so we can have a very good structure of the solution. Okay, so maybe we can see example how to use that. So the example is called Z channel. Okay, so basically the channel look like this. It's like a Z. Okay, so here's the input 0 and input 1, right? And here's output 0 and output 1, right? Clearly, if the input is 0, the output has to be 0, right? The probability here is 1. Right, and then when the input is 1, we say, okay, so with the epsilon, we can make a mistake, and the 1 minus epsilon we receive a 1. Okay, so this is basically the Z channel, and here we can just assume that P and 1 minus P be the optimal distribution. Optimal input distribution. Okay, and here, based on this structure, we can write down the transition matrix P, right? So basically, again, so the row represent the input, and the column represent the output, right? We can see that. So we have 1 here, 0 here, epsilon here, 1 minus epsilon here. Okay, so this is a transition matrix, right? Like the Banner symmetric channel or Banner irregular channel. Okay, so now what we're going to do is that we're going to compute. So now we have only 2 input letters, 0 and 1, right? Therefore, so we can compute 2 things. One is this guy, and the other one is this, right? Because we only have 2 letters, 0 and 1, right? Probably both of them are good. Right? Otherwise, we only have 1 letter. Then, how come? I mean, doesn't make any sense, right? So yeah, probably, and then now in order to know the capacity of this kind of channel, so what we do is the follows. We compute these two exactly and make them equal, and that will give you the capacity. Does that make sense? Right? Just compute this explicitly and make them equal, and then you'll find the capacity. Okay, so that's basically our approach. Okay, so yeah, let's solve the problem. So basically our goal is to see, okay, what is the best input distribution, right? So that's our goal, okay? So basically we only have one parameter P to solve. And then, after solving P, then we know the capacity. Okay, so now let's compute it. So let's compute this guy first, X, the mutual information between X equal to 0 and Y, right? Let's just use the definition to compute it. Right, so basically, so now it's X equal to 0, right? So we need to write the conditional distribution here, right? So P is 0 given 0. So the first 0 is Y, the second 0 is X, right? And then log P 0 given 0 divided by P 0. Okay, and plus P 0 given 1 given 0, and log P 1 given 0 divided by P 1. Okay, so that's basically the definition of the mutual information, right? And from here, we can see that given X equal to 0, and then Y cannot be 1, right? So basically, you can see that this guy is 0, right? And then second term disappear, right? We only have this first one, right? So first one, we can just plug in the value, right? So P0 given 0, that's 1, right? And then log 1 over P0, and that's it, okay? So now we can see that the only thing we need to compute is, we can ignore the 1, right? It's just log 1 over P0. So now the only thing we need to compute is P0, right? Let's compute it, see whether, so yeah, because now we know the transition probability, and we know the probability of P0 is P. So yeah, by the way, so this is the probability of 0, this is probability of 1, right? Probability of 0 is P, probability of 1 is 1 minus P, right? Then we can compute this P0 very easily, right? So P0 given 0 times X equals 0 is P, plus P 1 given, 0 given 1. P0 given 1 times the probability of 1, which is 1 minus P, right? And then we just compute it. So it's 1 times P plus, so from 1 to 0 is epsilon, right? So here's epsilon, 1 minus P, right? So that's P plus epsilon, 1 minus P, okay? So that's P0. Then we can see that, so this guy will equals to log 1 over P plus epsilon 1 minus P. Okay? Yeah, that's how we can compute this mutual information. And similarly, we can compute this guy, right? Yeah, this approach will be exactly the same here, right? We have P0 given 1 log P0 given 1. We have P0 plus P11 log P0 given P1 given 1, right? Now P0. P1 given 1 divided by P1, right? Okay, so now the difference here is that we do have a second term here, right? So we know the first term, this guy is epsilon, this guy is 1 minus epsilon, right? So here, P0, we know that's this number, right? So we plug that in, right? And for P1, it's just 1 minus this guy, right? And then, so we know everything, so we can compute it. So we don't go, the details on that. So I'll just tell you what that equals exactly. So it equals to epsilon, here epsilon P plus, you just plug everything in, right? So 1 minus epsilon log 1 minus epsilon, 1 minus P, 1 minus epsilon, 1 minus P. Okay, yeah, we just plug everything in and we can get it, right? Okay, so now the next step is that, okay, so we need to let these two mutual information are equal, right? So this and this guy will equal, right? Both of them equal to C prime, right? But we don't need to worry about C prime, so they have to be equal, right? And then, we can solve this, right? So I will not go into detail. So make them equal, and then eventually what we're going to get is that we have 2 power the binary entropy function h divided by 1 minus epsilon equals to this guy. Okay, so here you can solve for P, right? So this is the only function of P. You can solve it for P, and then you can compute the channel capacity. Okay, so that's how we use the theorem to compute the channel capacity. That clear? Okay, great. Okay, so now let's take a look at the joint typical sequence. So here we have 2 options. So one is we can consider a strong version of the joint typicality, and but here we follow the book. We consider the weak version, or we call that the entropy typicality. Right. So I have 2 ways to define the typical sequence. Right. So one way is to use a stronger version, which is types. Right here is a weaker version. We just use entropy to define the typical sequence and the AEP. Okay. So yeah, I'll explain why the other one might be better, but this one is used in the book. Okay, so the reason we want this is that we need to, the next step is to show the channel capacity formula, right? So why the maximization of mutual information achieve the channel capacity, right? So as before, we want to show that we need to show 2 things. One thing is achievability, right? We need to design a scheme to achieve it, right? The second thing is to show the converse or the impossibility, okay? Normally, for the achievability, we're going to use the idea of the typical sequence. Okay, that's why we need to introduce it, right? So now, different from before in the source coding, right? We only have X, so which is the source information that we want to compress, right? But now, for the channel coding, we have 2 letters. We have X and Y, okay? That's why we will need, joint typicality, right? Which is to describe the typicality relation between X and Y altogether. Okay, so let's see what is the joint typicality. Okay, so now, let's define X and Y, these 2 random variables, be 2 correlated random variables. Okay, so they're not independent, but they can be independent over time. Okay, so let xi, yi, where I is from 1 to n, be an IID sequence of pairs. Okay. Okay, so now things can be very interesting, right? So what we learned before is that in order to define the typical set, or define the entropy typical set, so we use the fact of the weak law of large numbers, right? So what we can show basically is that if we consider the self-information of X, right, and then if we divide by n, so it will converge to, when n becomes very large, it will converge to what? The entropy, right? So this convergence is in probability. Okay, and similarly, we can get y. Okay, so this is in probability as well. Yeah, here should be xn is a sequence. here should be yn, a sequence. Okay, but this is what we learned before, right? For each individual ones, it has to be true, right? But now we consider the joint ones, right? Then the mutual information, I mean the self-information between x and self-information of xn and yn, right? If we normalize it, so clearly it will converge to the entropy of x and y in probability, right? Okay. Yeah, we know this. Okay, but now, so how can we define the typical set? Right? Do we need to know? Do we need all of them, or only this is enough? Right? For one variable is straightforward, right? But now I have two variables. Okay. So now I want to define a typical set. Okay. Clearly, intuitively, if we say x and y are in the typical set or it's a typical sequence, then probably also want x to be in the typical set as well, right? But now the question is that, so can this guarantee this two? If we can, then we just need that, right? If we cannot, then we need all of them. Yeah, can I guarantee? Yeah, think a little bit. Okay, so meanwhile, I'll write down the definition of typical set. The joint typical set. Okay, for the joint PMF, Px and y, and we need the epsilon bigger than 0. The joint epsilon typical set of sequence pairs x, y is in this product space is defined as, so we use again this atypical, use A to denote typical set because it's entropy. Normally we use T to denote the strong typicality. Okay, what do you think? So it's a set of all x and y, right? Do we need all of them or just one is fine? Take a guess. All of them? That's a good guess. Why? It's a pure guess or you have some reasons? Yeah, I think it's, it's not very hard to see, right? So you can see, so normal, one thing we know that, for this guy, for this entropy typical set, it's an average concept. We just average on everything. Okay, so if this guy is true, still an average concept, right? We cannot guarantee that because this is a stronger condition, right? So we can, for example, let's say if x, y are independent, right? So this guy can be, higher, and this guy can be maybe lower by the same amount, and then the addition of them, the difference part will cancel out, right? So we can see that each of them is not in the typical set, but this guy is fine. Okay, just think a little bit more. It's not so difficult to see that. So in this case, so we have to use all of them. But if we use a strong typical set definition, right? So that is defined on each probability, each PMF value, right? Then for that definition, we'll only need that because that work on each value of the PMF, right? But here we'll only work on the average value. So this is weaker. Okay, yeah, but eventually, it's no big difference. So it just one is more convenient than the other, right? So here we need all of them, right? So when we talk about typical set, in this case, the joint typical set in this case, we need to guarantee all the three inequality. So this guy will be less than or equal to epsilon, and this guy have to be less than or equal to epsilon, and this guy I x and y minus hx and y has to be less than or equal to epsilon. Okay, we need to guarantee all of them. Okay, by definition, therefore, we know that if x, y, they are joint typical, then individually they're also typical. Does that make sense? Because it's definition, right? Okay, then we can talk about the properties, right? Similarly, so we're going to have all of the property that we talked about before. So the first property is that, we ignore the very first property, right? The very first property is basically definition, if you recall, for the single variable typical set, right? The first property we say, okay, so this has to be true, right? So it's from the definition. And so the next property is that the probability that the typical set happens. Yes, the typical set happens. Well, goes to 1 when n goes to infinity. Or, we can write in this way, the probability that the typical set will be bigger than 1 minus epsilon for any epsilon for sufficiently large n. Okay, so the first property basically means that the typical set occupied all the probability mass, right? So this is not surprising, right? Right. Okay, second one, next one. Do you remember what's the next one? So basically, we need, the point. So y is called AEP, right? Asymptotic equipartition property. It basically means that all the pair will appear with roughly the same probability. Right, for single letter case, for single variable case, so it's the 2 power of minus entropy. Right here, same thing. Okay, so second property is that for the single letter case, we know this probability will be bigger than or equal to or less than or equal to, bounded by this 2 power of n entropy minus epsilon, right, and bigger than the same thing, almost same thing, plus epsilon. Right, and we know that the py is also bounded by this. Right, and the new thing here is that pxy is also bounded by this. 2 minus n hxy minus epsilon. Here is 2 minus n hxy plus epsilon. Okay, so roughly speaking, the probability are all the same, right? So this is the second property. The first property, the next property is the what? The cardinality, right? What's the size of the typical set, right? So can you tell me? So what is the size of it? Say again?
Like 1 over the probabilities of this.
Yes. Yeah, 1 over the probability, right? So basically that's 2 power n hxy plus epsilon. Right, very good. The next one is, so this is a upper bound, right? We also have a lower bound, right? Lower bound, we need n to be large. So upper bound, we kind of don't need that for n to be very large, because when we compute the upper bound, we use the fact that probability is less than 1, right? But for the lower bound, we use the fact that probability is bigger than 1 minus epsilon when n is large, right? Then we can see that, so this guy x, y, bigger than or equal to 1 minus epsilon, 2n h x, y minus epsilon, okay? So basically the size of that is, roughly speaking, 2 power n times h x, y. Right. Okay, any questions? Okay, so the next one, you didn't see that before. So this one's kind of interesting, right? So basically, so now we say, okay, so if x and y are generated using the PMF of pxy, so this is what is going to happen, right? But now let's say, okay, what if, so x and y follows the marginal distribution, but they are independent, right? Let's say, what if I say x tilde follows a px, and y tilde follows a py, right? But they are independent, right? So basically it means that the joint distribution, distribution of x and y, so this is px times py, so they're independent, right? Then if we sample this distribution, so can the pair of x and y in the typical set of the pxy? Yeah, do you understand what I'm saying? Right. So when we talk about the typical set, right? So this xy generated from px and y, right? The joint distribution. But now let's say, okay, the marginal distribution is still the same, px and py, but they're independent. And then we generate these pairs, x and y. So would that be typical? Or what is the probability that this pair of x, y will fall in this set? Right, so this is a very key of proving the channel capacity. So later on, you're going to see that. So our decoding is very easy. So we send a code word generated from some distribution, right, px, right, and then we receive y, right. So the way that we're going to decode is to see whether they are typical or not, right. Say, okay, we know y, we find a typical, so we find an x that is jointly typical with y, right. If we can find this x, and then we're done. So that's the code word we transmitted, right? But now, the problem is that, okay, so if some independent x is also jointly typical with y, then we have trouble, right? We don't want that. But can that happen, or it cannot happen, right? So that's basically this property is what this property is about, right? So let's write it down and see whether it makes sense or not, okay? So first of all, we let the pairs xi tilde, yi tilde. This should be small, I think. It's a realization. Let's see, x tilde, I, yi tilde, and I from 1 to n, so this be an IID sequence, okay, of copies or samples of x tilde and y tilde. Okay, and then the probability that x, here's bigger one, x n, y n. So this is in the typical set, right? Turns out that this probability is definitely not zero, right? Why is not zero? You can think about this, right? So if we generate an x with very high probability that it will be typical, right? If you generate y, it'll be typical, right? So now the total size of this pair, because they are independent, right? The total size of this guy is 2 power hx times 2 power hy, right? So that's the total number of such sequences generated using this independent distribution, right? But when we generate the pairs all together, right, the size of it, the size of typical set is 2 power hxy, right? Therefore, normally the summation of the individual entropy will be bigger than the joint entropy, right? Therefore, some of the pairs will be in the typical set. Does that make sense? Right? So now you may guess, right? So what's the probability? Can anyone guess? Basically, the probability that h of xy minus hx and minus hy. Right, what's that? Mutual information. Minus 3 epsilon. Okay, we're going to show that, don't worry if you don't see that. So this is the upper bound of the probability. We have a lower bound as well, okay? So, and for lower bound, again, similarly, we need to show that for sufficiently large n, right? So the lower bound of this guy you can make guess, right? So we have 1 minus epsilon here as usual, and then we still have this. Plus 3 epsilon. So basically it means that the probability that this pair of x and y is typical is 2 power of n times the mutual information between x and y. Okay, so that's the probability. Okay. Yeah, basically the meaning of 4 tells you that the probability that, let's say, yeah, maybe I'll explain it this way. So the meaning, this is very important. Meaning of 4, okay, is as follows. So basically, let's say we have a communication channel, right? And we transmit a code word xn, and we receive a code word yn, okay? And the code word basically means that we have x1, x2, up to x capital N, right? Remember, each of them can be understood as a row in the matrix, okay, of length n. Okay, and then we say if xi is transmitted, right, then it will follow the distribution of pxi and y, right? It will follow this distribution. Okay, and then we can see, okay, so I receive a y, and then I can find something that's joint typical with y, and then we're done. Okay? And of course, you may think, okay, what if there are like 2 x's typical, joint typical with y? Okay, then we're not good, right? But we're going to show that this will not happen. Okay, don't worry about that. But what is bad is that, okay, so now what if some independent x is joint typical with y, right? Let's say, what if for some I and j, for some j, that is not equal to y, okay, and distribution of x, j, and y, so they are independent, right, because that is not from I, right, so they are independent. And then the probability that xj and y are joint typical in the typical set epsilon n x, y, right? So this probability is roughly equals to this guy. Okay, so that's the meaning of this theorem. Okay, even if they're not, they're independent, then we're not good enough. Okay. All right, and yeah, the proof is really not very hard. We're almost time, so I will just prove one direction, then you can finish the other direction. It's almost the same. Okay, you can see how we prove it. X tilde y tilde n, right? That is in this. So I want to compute this probability, right? So one thing that we can use here is that, so px and py, so here they are independent, right? So we consider all pairs in the typical set, and then this is the probability that will happen, right? They are independent. Okay, and then, so we can upper bound it by the follows. Okay, so we know the probability of this guy, and we know the upper bound probability of this guy, right? Because this guy has to be typical, and this guy has to be typical, right? So we have this for x, and this for y. Okay, so you can see this is how these 3 epsilon come from. We have 2 epsilon here already. Then we're gonna have another one. Okay, so then we can bound it as follows, right? So now you can see, so this is not a function of x and y anymore, right? So it's independent of this particular x and a particular y, right? Then summation, we just need to count how many number of items here, right? So it's in the typical set, right? So basically, this is the size of the typical set. Okay, and then times this guy, we can combine them, and hx plus hy minus 2 epsilon. Okay, right, and then we know the size of it, right? The size of this typical set is a joint typical set, right? So basically, that is less than or equal to 2 power n h x and y minus epsilon plus epsilon minus plus epsilon, right? Because upper bound. Okay, and then we times this 2. Okay, and then we can combine them, right? So basically, we can write this guy as this hx plus hy minus hx and y, and then minus 3 epsilon. Okay, and then we can see clearly that, so this guy is nothing but the mutual information. Right, so this is a formula, one of the formulas to compute mutual information, and then we're done, right? So this is how we prove it, right? For the other direction, it's exactly the same, okay? So we don't need to repeat that. Okay, great. So yeah, let's finish for today. So next lecture, we're going to prove the channel capacity theorem.